Okay, so let's say, for example, a square has a side length that is increasing at a rate of 19 inches per minute. Okay, so what is the rate of change of the area? When the side length is 5 inches. Clean that up a little bit. Okay, so now we just have to figure out what formula we're going to start with. Okay, so we know we have a square. So square, which, remember, all sides are equal. Okay, so we'll call this side S. So since the area is length times width and all sides are equal, that means your area is equal to S squared. Okay, so we're looking for the rate of change of the area with respect to time. Okay, so the derivative of the area with respect to time is equal to the derivative with respect to time of S squared. Okay, so your dA dt is equal to, we're going to bring down our 2, 2s, times ds dt. Okay, now sometimes you might want to find out what's given and then solve for your factors. In some cases, you might want to solve for your factors first, then go through the problem and find out what's given. So here, we just solved that first. Now we're going to go back and find out what's given to us and what we can just plug in. Okay. Now we know the side is increasing at a rate of 19 inches. So we know your rate of change of your side with respect to time is 19 inches per minute. Okay. And we know we want to find out exactly what our rate of change of the area is when our side is equal to 5. So we know our side is equal to 5. And just the line through is just to make sure, because I draw my 5s and S's pretty quick, and I don't want you to confuse one for the other. So if you see a line through it, that's an S. If not, it's probably a 5. Unless it's an S, I forgot to draw the line through, then hopefully it won't mix you up. All right, so rate of change of the area with respect to time is equal to 2 times S, so 2 times 5. times your rate of change of the side with respect to time, which is 19. Okay, so that would be rate of change of the area with respect to time. 2 times 5 is 10, times 19 is 190. Okay, so the area is changing at a rate of 19 inches per minute.
You mean 190 inches?
Oh, 190, thank you. All right, any questions on this one? All right, let's do another quick example. Okay, so this time, let's say we have a triangle. Okay, has a base. Uh-oh, clean that up a little. Okay, so a triangle has a base that is decreasing. At a rate of 19 millimeters per minute. Oh. And a height that is constant. Okay, so what is the rate of change of the area? Of the triangle when the height is equal to 4 millimeters. Okay. So we know that since we're dealing with a triangle, the area of a triangle is equal to 1/2 times the base times height. Okay, and we know that we're looking for the rate of change of the area, so that means we're just going to find dA dt. Equals 1/2 base and height. Okay, so we know that rate of change of the area is your dA dt. So we just apply dt to both sides. 1/2. Don't really need that just yet. Derivative with respect to t of the base times height. Okay. So here, we're just going to use the product rule. Okay. Rate
Why
of
are we taking the derivative of the height when the height is constant?
just practice. Yeah. Plus, we don't know exactly what the constant is, but we know it's constant. Hmm? Oh, they did give it. Never mind. Actually, still practice. It's just one of those things where it helps. Okay, so you have 1/2. Okay, so you have the first times the derivative of the second. So the base times the derivative of the height plus the second times the derivative of the first. So the height times the derivative of the base. Okay. So this is why I kind of worked it out so that this would hopefully make sense. So you have the base times the rate of change of the height with respect to time plus the height times the rate of change of the base with respect to time. Or you can multiply both by 1/2 if you want to. Okay, and the reason I went kind of the long way is because if you look, and if you see that the height remains constant, the rate of change of the height with respect to time is equal to 0. Okay, so that's kind of why I went the long way instead of plugging in the h equals 4, which we could have and pass by all the work, but this way if the rate of change of the height is 0, that disappears anyway. Equals your height. I don't really need that parentheses there. Well, 1/2, that would help. Times the height times rate of change of the base with respect to t. Okay. So now, since we know we're looking for our dA dt, we have our 1/2, we have our height is equal to 4, which is given. And we have our base that is changing at a rate of 19 millimeters per minute. Give that a little more room. So the rate of change of our base with respect to time is equal, we know it's 19, but because it's decreasing, we're going to make it negative. Okay, so now we just plug everything in. So we have 1/2 times our height, where h is equal to 4, times the rate of change of our base, which is negative 19. Okay, so 4 divided by 2 is 2. 2 times negative 19 is negative 38. So the rate of change of the area with respect to time is equal to negative 38 millimeters per minute. All right. Any questions on that one? Okay. So you can see here that even though we ended up with an equation that had the base, because that disappeared, we didn't really need it. So. All right, leave that up for a few seconds. All right. And we'll do one more. Okay. Okay, so let's say the volume of a sphere is increasing at a rate of 555 cubic centimeters per hour. Oh. Let's say, I'll just write it as cubic centimeters. Okay, so what is the rate of change? Nope, that should be millimeters. Why do I keep putting centimeters? In millimeters per hour of the radius when the radius is, why does it seem like I did this one already?
We did the balloon one.
It does seem like I did this one already.
Yeah, you did one that was virtually the same, but it's a balloon.
Yep, that's right. Okay, I'm like, okay, I know I'm not losing it. When the radius is 5 millimeters. Okay, and I'll give you a few minutes to start on that one. That's why I picked one similar. Now I'll remember. And you just give an exact answer. So you don't have to worry about decimals or anything. Oh, okay. Remember, you're going to use the same volume formula. right, so let's go ahead and work this one out. So once you have your formula, you can just go ahead and differentiate both sides. Rate of change of the volume with respect to time is equal to, we can just bring all our constants out to the front. So we have times the derivative with respect to time of our radius cubed. Okay, so that gives us rate of change of the volume with respect to time is equal to 4 over 3 pi, bring down our 3, subtract 1, times dr dt. And just like before, our 3's canceled out. Rate of change of the volume with respect to time is equal to 4 pi radius squared times the dr dt. Okay. So now we go through, we find all of our givens. Oop, don't really need the s there. Okay. So we know the volume is increasing at a rate of 555 cubic millimeters. Okay, so we know volume is increasing. So the rate of change of the volume with respect to time is going to be a positive. You don't have to put the plus there, but okay. And we want to know what happened when the radius is equal to 5, so given is our r is equal to 5. Okay. So we go ahead and just plug it in. Okay, so you have 555 is equal to 4 times pi times r squared. Here's our 5 squared. Times your rate of change of the radius with respect to height, which is what we're looking for, the rate of change of the radius. So it's the only thing we don't have, which is what we're solving for. Okay, so that gives us 555 equals 5 squared is 25 times 4, 100 pi times dr dt. Divide both sides by 100 pi. That cancels out. So the change in radius with respect to time is equal to 555 over 100 pi, which if you divide both by 5, you get 111 over 20. Well, 20 pi. Millimeters per hour.
Millimeters cubed per hour, right?
Nope. Yep, the volume will be cubed. Yep. I know, I remember doing the exact same thing before. I just always had to remember that the volume is cubed. All right, so any questions on this one? All right, so we're going to stop there. Like I said, I don't want to add anything else.